recording. So when you have a project in Visual Studio, you can click on Properties, then go on Qt Project Settings, and then under Qt Modules, when you click on the arrow and then on Select Modules, you get a window where you can select Qt Network and many other components. You're welcome. Any more questions? Okay. If there are no more questions, then let's start with something new today. So, since we only have 3 more lectures, I was thinking that it might be interesting to show you a few more exotic techniques. So, something that you usually will not see in the average programming course. So let's create a project for that. Something new. Just a normal console application. Okay. So let's start with something very simple. Let's say we want. So first of all, we will include Windows 8 so that we can use all the different Windows classes. And let's do something very basic, like for example, just show a message box. Message box. Okay. This is just as a sample of calling some function from a library. So when we look how this works, put a breakpoint here, and then see the assemblies. This assembly, then we see that we have a call. We have a few more things which are not needed. Let's first disable them. We don't want this. And just this. And we don't want this, and we don't want that, so that the generated code is simple. There's, I think, one more thing which we didn't disable, but that's good enough. So we just prepares the registers, so the values that we have passed here are put into registers, and then it makes when the focus on this window, it doesn't go step by step. You need to put on the debugger window. Then it just makes a call to an address in a library, in this case user32dll, where the message box function lives. And all the APIs of Windows live in such DLLs. And also if you have programs which are using third-party libraries, they also would be using the same mechanism. So you have DLLs which export functions, and your program loads the DLL and then calls the function. And depending how the DLL is integrated, it's either loaded automatically. So like here, that you can just write the function name, or you need to first load the DLL and then load the address from it, as we did with the in the interface project with our plugins, where we load the plugin and then get the function with getProg address that acts as a factory for our object. So far, so good. Now, you might have, in some exotic edge cases, find yourself in a situation where you would want to change how either a library interacts with the operating system, or a third-party program interacts with some library. So basically, where you would want to be able to modify the communication between a process and the DLLs that the process is using. And of course, the same technique can be used to change internal program behavior, but there the problem is that you don't really get a nice start point, so you don't know the addresses of the functions unless you have the whole debug database. So normally you can do such things only when between DLLs and the applications are using, or if you have a DLL that uses another DLL, etc. So each time where you have an address of a function, that can be resolved with this get procedure address, or which can be resolved automatically like here. So what we want to do is we want to redirect the function call to MessageBox to our own implementation of MessageBox. So first of all, we need to exactly know how this function is defined. So we can just, in this case, we just can control click on it, and then we go to the header file that is provided where it is defined. And there are also undocumented Windows functions, so there are sources where you can find this information. The first one tells that it's imported from a DLL. We don't need that. Then we have just a return value. The Win API is a preprocessor definition which specifies the calling convention, and it's in case here it's defined as standard call, but effectively on 64-bit there is just one calling convention. If we would have if this would be 32-bit, then it would in this case also use STD call, but you would have a few more calling conventions available, and if you would not specify the right calling convention, that would cause an incompatibility with 64-bit, since all calling conventions effectively are the same, or rather there is just one, and the keywords to differentiate them are just without a function, so that the code just compiles. Then if that would be wrong on 32-bit, you would get a crash. On 64-bit it doesn't matter, so it can be a common mistake where you forget to specify this, and in one bitness your application works fine, while in the other it crashes. Okay, so we have some function, and let's say we don't want to print any text, we just want to quit. So and of course the problem is that we need to call it something else than what is already defined, like for example my message box. And now the trick of course is that that was wrong. Yeah, okay, I think that was ID. Okay, yeah. Basically this dummy function would always say that we have pressed OK. So to demonstrate this maybe way better, we can also make this a bit more convoluted. So let's say if message box title question and yes, no, if this is IDS, then you just crash it, or just return an error code. Then another message box 0, L okay, and icon exclamation mark. Then in the other case it will be a success message, so 0 help. And a scenario, there are many scenarios where you might want to modify the communication between some application or some library with the operating system. But for example, one use case you might encounter would be if you have some very old control program that uses Comport to communicate with some hardware, and of course you don't want to buy new hardware just because the application is old. And many old programs, they only supported Comports, I think 1 through 12 or 1 through 8, I don't remember. And that had historic reasons. On older systems you couldn't have more ports, but on modern systems you can have as many ports as you can stick into a USB port. So you could have up to over 100 USB to serial converters, and each of them will get an own port, and then you would have of course high port numbers. And of course one way would be to just define for those applications, for those hardware that needs a lower port number, just to use the lower port numbers, but then it's just a question of luck whether you have enough lower port numbers for the old hardware that you want to connect. So what would be a useful use case is if you can have an application, tell it to use COM1, but then when the application actually tries to communicate and open COM1, you would be able to intercept it and make it that it would in reality open, for example, COM20 or something like that. So these are this would be a use case where such an ability to have a say is quite useful, and here we will just demonstrate with the message box function, since the message box function is well, it's a good target for demonstration, and you see the result immediately. If you would try to do something with real hardware, then of course it would be much more complicated and not as obvious whether it's working intended as or not, since we only have here a remote session. So we will create a function which will be responsible for manipulating the communication. For now we will do everything in one project, and later we can demonstrate how to do that in a way that does not require to be able to modify the original application at all. Because usually when you would have the ability to modify an application, then you would not have the problem in the first place. So let's create a function, or let's call it hook message box. Of course we will need to do this modification before we do it, and then let's see where we start. So first thing what we will of course need is we will need to have the address of the message box. Let's see what's a good strategy so that this is as simple as possible. So for starters, we will only want to redirect the call to message box to their own function, and we will not care for anything else. So let's create a small helper structure. Onion. So just to help us assemble some instructions later on in the most convenient way we can. Okay. So what we will want to do is we will just want to overwrite the code which has been loaded into memory of message box with a code that would instead jump to our message box. So we can start with getting the address of message box. So let's add a helper variable where we will cache the address. So it's going to be a void stern. Message box v is equals message box v. If we would not have a function which is loaded automatically by the linker, we could here instead use the get process address as is typically used with DLLs, where we can then get an address of a function DLL which is exported. Unfortunately, this, as already mentioned, only works with functions that are exported. So internal functions of a DLL cannot be resolved this way. So we want to and a function which takes over is usually called editor function. So we use our helper structure pb is equals ochar. So we just make this hold the address. Make this hold the address, and now when we start overwriting things, we will be able to increment it with the right offset. So of course now the challenging thing is to know what to write to the memory, and they are some nice online tools that we can use for this. This one is good. We'll put the link into the link. Actually, we could put this here into the comment as well. So this website allows us to write some assembly code, and it will provide for us the assembled version of the code. And the idea what we will want to do here, once we have our box, will be we will want to have a well, in the end we want to jump somewhere, so jump, and for example we want to jump to the register array X. So first we need to write the address where we want to jump to in this register. So move absolute rax, comma, and then some address, some 64-bit address. So that would be like the simplest thing we can have. So let's see how this looks when it's compiled. Of course, we have the comment here, and it spits for us out the binary representation of these instructions with some, I mean this, yeah. So as we see, the first one is made up of how many is it? 10 bytes, and of course we can. The important thing to notice is which of those bytes are our actual address. So this number here should, since it's 64-bit, should be prefixed with the right amount of zeros. So the zeros we have here, and then the rest will be these bytes. So effectively we have two bytes of opcode and 8 bytes of data which go into the memory. So asterisk pb punct 2 bytes is a word is equals 0x, and now we have to be careful because the byte order that you see well in memory is kind of reversed to how the bytes, to which places the bytes take in a hexadecimal representation of a number. So on a computer, the first byte is always the least significant one, while when we are writing a number, then the first from the left side is of course the most significant one. So here we'll need to swap them. So it will be B8 48 instead of 48B8. So this is our move absolute rax, comma, part of the instruction. And now we want to write and what we also want to do is we want to increment the position to the next byte. And since we are using a union, effectively we can use any of the fundamental types, and this way, so the plus plus automatically addresses the next one for the next operation, and the asterisk dereferences the previous value so that we can write at the right position. So now we'll write code.pq, that's the 64-bit number. This one will be equals to, well, first of all, 64 in the cast, and here we can just write directly the address of our message box, my message box V, which is then the target. And the last thing what we need to do, of course, is to jump there. So it's this one, and it will be 0x. Again, we swap the bytes. A0ff. Zack, jump rax. And with this modification, in principle, we already have intercepted the function. Now our function always just says id OK, which is not necessarily what we want, but we could make it a bit more complicated. Plus, of course, there are other aspects to the whole mechanism, being that if we would run the code as is, here it would crash because the memory where the function lives is not writable. So we can just run it just to see the error. So first thing, before we actually can write to this memory, is we need to change the protection on the memory. There is a function for that called virtual protect, which allows us to change the protection state of some memory. So first define a variable where we can store the old configuration for this memory page. Then we can invoke virtual protect, and we specify the address where we want to change the memory protection. We also have to specify the size. In this case, let's go with 32. That is a bit more than what we need. Generally, the way memory protection works is that it has only the granularity of one memory page. So it has a granularity on most systems of 4 kilobyte. But of course, some address might be like on a boundary between two pages. So the idea how this works is that you specify an address and the length, and then it will change the protection of all the pages which are involved in this memory range which you have specified. And then it will, of course, it wants to know how to change it. So let's go with page execute read write. And execute read write is not what you would want normally for pretty much anything, because execute read write means it can be written and it can be executed, which is a potential security risk. So what we can do is we can save the old protection state into our temporary variable, and later, once we are done with the modifications, we can restore it to the original value so that the system will be secure again. Now, since this is a very primitive demo, let's at least slightly make it more sophisticated. So if what's sample lp text, comma. So if this, so if our function, if the function sees this question, it will automatically return ideas, and in all other cases we just return OK. So, and of course first we can comment this out and see how this would normally work. Well, it gives you a question, then it, oh wait, did I, yeah, I want to say I wanted it to fail. Fine enough. But we also see the return value if we make it fail, that it here return code FFF, so in -1. And now if we activate our hook, then it should not show any message and just silently terminate, but with error code 0, since we would in principle take this branch, since this function should return IDS. Oh no, I need to return ID no, for it not to fail. It failed again because if you press yes, it fails obviously. So it's, and now if you return no, then it doesn't fail. And at this level, of course, this is interesting, but what we effectively did is we broke the original function, and if you would want to do the earlier example where you would want to redirect the comport number, then bar for special cases, we would effectively not be able to call the function that we would want to call, because what we would want to do in this case is just to change the parameter while keep the rest of the execution normal. And in this case, of course, this would not work as it should, because effectively this function is no longer functional. There are, of course, ways how this can be mitigated. So one strategy, for example, would be to make a backup. So let's do this first. Return original message box here, let's call that. Let's count how many bytes we are using. 10. Well, we use 12 bytes, but let's save, or let's go with 32. So we save more than enough bytes. So before we do the modification here, we would memcopy target source, 32, and then we'll of course need a function to reverse this. Unhook message box, and there it will be somewhat similar. Just that that scenario we could here use this as well, doesn't really matter, just the address. But the of course difference is that we need to do this inside the path that allows us to write to this code section. So now if we define this function somewhere that we can use it, we should put all the functions so that they're accessible. So in this special case, if we know that we only want to bypass the first question, then we can, while we are already doing our own execution, we can unhook the function. So basically just restore it by overwriting the original data back to the function, and then it should basically ignore this question, answer it for itself with no, and then this line should be executed normally already without any modifications. And you see, it is now saying that everything works fine. And for a very simple use case, this would be good enough. Of course, there are more complicated scenarios where such a mechanism could fail. So, for example, if you have more than one thread and many threads would try at the same time to show a message box, then you could override the memory while one of the threads is in process of executing something that is written there at the top of this message box function, and then you would basically more or less change the opcodes midway while it is executing them, and that would of course not be good. A mitigation for that would be well, twofold. One thing you can of course do is you can suspend threads, so that there is no thread running in the process except the one which is doing this suspending, and then you would need to check for every thread that you have suspended whether it is just right now in process of executing this guarded code section. If it is, then you basically would either need to realistically the only thing you could do is to just let it execute again and then suspend it a bit later in the hope that it is now doing something else. Trying to modify it in some way is probably not reasonable. You could in principle of course try to because you know the address which a thread is executing, and you get and you can read and write all the registers that the thread had set while it was active. So in principle, if you would know exactly which every instruction is doing and how it should be changed in order for everything to work out, then you could manipulate it such that it would work that it would work again. But this is an approach which is generally not recommended. So either just don't unhook the functions or have an internal mechanism that would take care of that. And of course, another much more complicated situation is what if you need the message box function or whatever function you have hooked from inside of your detour function. So let's call it not my but message box detour message box faded is nicer, right? So you might have a scenario where you actually want to from inside this still use the original function. I mean, in this case you could still unhook at the very beginning and then let it do its thing. But the other scenario that you might have is that you might have a scenario where you have multiple threads using the function and you actually want this function to remain hooked and be able to decide which operations you modify or not, because in this case you're kind of waiting, you are basically expecting that the first instruction you will get will be the one that you want to modify and then nothing else. So it is a very limiting approach. So what we would want is some ability to not have to restore the original function, but still maintain the ability to call the original function. So that sounds a bit more complicated, but that can be done. So what we will do for that is we will first define us a helper type so that we can create pointers to this type of function. Let's call it just or t message box. It just needs to be something that is not yet used. And now we have the data type t message box, which is a function pointer to something that we already had the original message box. Then let's call it message box with trampoline. Okay, and for starters, this can start out as null because it doesn't have yet a function body. Okay, so in the idea is now that we will be able to call this instead of message box if we want the functionality of the original message box function. So of course we will need to prepare it before we start messing with the original message box function. So let's do it somewhere here. And such a function which or rather such a code snippet which will enable us to call the original function despite the original function being modified is usually called a trampoline. And the important trick of this trampoline is that it works without continuously rewriting the function. So if we would have a single threaded case, the way our detour function might be implemented is that it would always first unhook, then do its thing, and then rehook before returning, which obviously would only work in a single threaded sort of use case, but we want to be multi-threaded, so let's do that. So first of all, we will need to have some address for our trampoline. And we would want this address to be as close to the original function as possible. So first we will just assign it the address of the original function. We can add some offset because we know that we cannot have it at the right offset anyways. This will be from target. No, that for starters. First, let's do it differently. So we start a set on the address of this thingy, but we don't really know how far we need to go to get it. So we will let this run as long as trampoline address remains null, and we will have an increment of x 4 kilobytes. So we try to allocate memory at this address, and then we just continue in the increment of 1 page steps until we find some memory space which is not yet allocated, which is close enough. So this thing is equals we need a cast get well alloc address. Then we want let's say 32 should be large enough as well. We'll see. And we want to allocate this memory with a few flags, mem commit and mem reserve, and we want again page execute with write. So let's copy that from here. Okay, and the way this works is that we try to allocate memory at a specified address. If it succeeds, then it returns it. If it fails, it returns null. So just by looping a few times through this, we will get an memory block which is close to our original message box function. Okay. But before we do that, we should so the way this trampoline is supposed to work is we will inspect the original message box function, we will copy a portion of it, and we will then relocate this portion to our own memory, and then at the end of this portion let it jump to the original offset in message box. So basically the top of the function is overwritten by us, but first we have saved the top somewhere else and made and arranged it such that it can be executed, and then we'll jump to the unmodified rest of the function and we'll be able to continue execution as if nothing had happened. So at least that's our plan. So before we continue, we will disable the hook and just quickly inspect how our message box is implemented. So we just click here and just step until we jump in, and then we can just copy actually the whole function if we want. So here, since we only see the address, we can load symbols. So that we actually see the symbols, that is a bit nicer. Right, so here, create the trampoline version function. And we can also see, so we know that we would overwrite the first 12 bytes, so until here. So basically we can go until this part, and the rest should be not longer altered. So here will be our trampoline target. So this will be the address where we want to jump, so that we can continue the execution. So we can write this down. Oops, that should be capital. The trampoline target is then of course our message box fee plus we count I think 14, so plus 14, and as long as this is less than what we are writing here, so in total we can write it down. That was 10, 12. So that we keep track on how much we have overwritten. Okay, so we have our trampoline, so let's continue. So we have obtained, so we know what we wanted to do. We have obtained an address close enough. So the next step will be to assemble the trampoline. Again, we are doing this by hand. Code.pb is equals first number one is equals Stern message box for trampoline. So each time we assign something to PB directly, we are changing the address on which we are working with our helper union here. It's a bit annoying, we don't really have enough space on the vertical screen. So asterisk punct code punct. First one is what? PD plus equals null x, and then again we need to reverse the order, so it will be 38 EC 8348. So this will be, and we always write down what is what. Keep track. Zack. Yeah, it's nicely lined. Okay, the next one is this XOR operation, which is unfortunately a non-power of 2 amount of bytes. PB plus is equals 0x45 33 and db. this is just this XORing a register with itself is often used to clear it, because the result, no matter what was in the register, will be 0, and it's quite fast. Okay, then we have the compare function instruction. Again, it is a longer one, so make pb, 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 and then the last one will be pd. Okay, so here we have 0x44, oops, then colon 0x39, 0x1d, 0x6a, and then wait, I don't want too much. This one will already be the value. That is 0, 0, 0, 3, f8, 6a. Oops, f8, 6a. And there is a catch to this, because the way we have done it now, it will not work, because this value here is a relative position. So when we are at a different offset, when our code is located at a different offset, this value will need to be changed. But for now, let's run into the bug intentionally. What we also can do is, for better illustration, we can take this code and see the proper disassembly, because the Visual Studio disassembly is a bit simplified. Okay. And what we see here, what this really is so subtract XOR, compare with taking a value at this address, and the address here is written properly because it's the instruction pointer plus an offset. Let's see if we can actually make this show us the right thing. Where were we? This one was the right one, so let's go again. The thing is not longer running. No, it is running. It should. Right. So here we don't want symbol names. Don't help. I should just know. Now we cannot. There's nothing we could change to make it actually show the proper disassembly, so that here it would really write down the this thingy. So I said this is not really made. It's really just made for debugging and not for analyzing of what's happening there. So actually, what we could do is we could also copy those lines here, so that we at least remember what the actual thing was. The first two ones, of course, don't change. Only the third one is different. Wait, we have one. No, that's an OSP. Where is the Google comma? Forgot this up here. That looked suspicious. Yeah, now we have everything. Okay. Right, and of course, what we also need is we will need to jump to the original code. So this part we can copy from here. We just change the jump address. And the jump address will be the already defined trampoline target. But as mentioned, this, if we try to use it, will end up in a crash. So let's run it. No, it will not, because we are not using it. Are we? What did we? break that. Our allocation here doesn't work, so why? Address message box fee. We failed to allocate the right memory. Address commit. Oh wait, that's the wrong. I said we want memory reserve. I just typed re and then pressed tab and it made the wrong version of it. Yeah, now it works fine. But as mentioned, I think we are not using anything anywhere. So for now, yeah, it will just silently close. So we need to use our trampoline. So we go to our message box here, and the idea is that we just, unless we see that we should provide an own operation and replace something, we can use then the original function. We could also use it to change the caption and show something else or change a parameter. In case of the comport example here, we would just change one of the input arguments and then call the original function with the changed argument. Okay, but as said, first let's run into the crash, and as you see here, we crashed at some address for which there are no debug informations available. View, and this is our CMP function, simply because the offset, the relative offset to the instruction pointer is not valid. So what we need here is we need to calculate the displacement and then take this into account. So for trampoline displacement is just uchar for our trampoline message box minus of the original function. This should be capital. Okay, so trampoline displacement, and to make it where was it? Jump here was the value, and to make this here work, we just subtract the displacement, and then effectively the value which the relative value which ends up here should be compatible, and the function should work properly. This is also the reason why here we want to have a memory block which is close to where the original function is, such that a possible displacement will be less than 4 GB in distance, because if it would be more than, actually it should be less than 2 GB, because it's a plus minus offset, so it's a positive or negative, and if it would be more than that, then most of the instructions that you have in x86, they do not take offsets larger than 2 GB. So this is a limitation. There is only a handful of functions which you can use, which take actually a 64-bit number to work with. Of course, all the numbers they operate on register-wise are 64-bit, but numbers that you can have written as part of your code are in this case limited for most functions, for most opcodes to be 32-bit at most. And an exception here is this move absolute, where we can load a 64-bit number into the rex register. Other approaches, of course, would be to read the values from an address, so that we would. So what we could do is we could use another register, one that is unused, then load to this register the value from another register, so we would already need 2 registers, and then to the comparison, but it would be much more complicated. So this way we really keep like the original code except for the offsets, which is the least invasive approach, And now, of course, as mentioned, it should work fine. So when we run it, it just tells us that app runs fine, and it is suppressing this message box. And we could also maybe add here some other message boxes to demonstrate it better. So we will throw a few error messages. So that could also be a scenario where you have an app that in principle works, but for some reason is throwing except errors, and this so this is annoying, and you want to get rid of it. So you want to suppress some errors. So here we'll modify our detour function such that if we could of course evaluate the text again, but let's go with something simpler. We just check if type is contains the exclamation mark a bit, then we just return ID OK. And now if we run it, of course it just says app runs fine, while if we would unhook our hook, so the unhook function still works after we have bypassed this code block, then it would still throw the 3 warnings before it says that everything was fine. So that's that. Was all that clear? Any questions? Okay. So if there are no questions, then of course the next apparent question is how would we do that with an application that we want to somehow modify, which we cannot just recompile, because I said if we could recompile the target application, then the whole operation here would be unnecessary. Well, that can be done using a DLL. So on Windows there are ways how you can make a DLL being loaded by another process. You can force a process to load the DLL within certain restrictions. And there are also tricks how you can load a DLL into a process really targeted. So there are ways where you can register DLL such that they will be loaded by all the processes on start, which might not be what you want if you just want to modify one particular process. So the more reasonable approach is a loader approach, so that you have an application that will start your actual application and then will make it load the DLL at the right moment. So let's start with implementing that. So we will do this by adding a few new projects. First we will add the loader. And then we'll and then we'll add the DLL. And we'll call it hook DLL. Okay, so when we create a DLL project, it creates this DLL main. This is an entry point which on the DLL is called for a couple of events. In this case, you see here that it already has cases to handle process attach, which means the moment when a DLL is loaded into a process, or rather when it's done loading, then the attach thread and detach thread. So each time in the process a new thread is created, all the DLLs within this process are notified that a thread has been created. This is not something that usually is helpful, but apparently there are use cases also where this is quite useful. So if you would have something that wants to maintain for every thread some state information, then you would of course want to know when to allocate new state information and when to clean them up. So this, while in most cases not so interesting, in some is very, and of course we have here this process detach, which is called just before the DLL is unloaded. So if the DLL would dynamically allocate some memory, then you would want to use this case to clean up your resources so that you don't leave some memory behind in the process if you are getting unloaded. Okay, and we have here our DLL loader, so this doesn't have yet any content. So first thing we will do is we will copy all our code here. So this doesn't happen, this doesn't happen, and this gets moved. So we just leave the program untouched the way it would be originally. Just put it in here for now. Do we have already Windows H included? Yes, Windows H is already included, so we can we don't need to extra include it. Okay. So the way Visual Studio works is that if you compile those projects, all of them will end up in the same folder, which for testing actually simplifies a few things because we don't need to mess around too much with paths. So you see we have here our DLL, our DLL loaded, our hook test application, our target application. You can also configure properties here. The project dependencies, this is quite a good thing because what we will want to do is we will always want to start DLL loader, and we want the other things already at this point be compiled and ready to be used. So we'll say this was a starter project. Sorry, that's the wrong one. Look there, this one. Set a startup. Oops. Set a startup project. Then this will be started and we'll do all the other things. So first thing we want to do is of course to define the path to our DLL and to our target program. So let's just create a char array. Oops, max path, which will contain. Here we need to inc Windows. Here we need Windows H. Max path is defined there, and there is the get module file name v function, which in principle gives us for every DLL, if you have its handle, the address, the path from where it was loaded in any given program. And if we want to get it for the application itself, we just use null. Then we'll get the path to our own process path. We have to tell it, of course, how much bytes are available here. So in case it would be longer, we don't want to have a security issue. But since we are not very security minded when doing such things, CSRCHL, we can do it here a bit dirty. So this gives us the full path, so including the file name, but we don't want the file name. So we use the white char search reverse, and we are looking for the last occurrence of \\, and we just assume that this will be successful, which we should never do. We should have a proper check if this is null, and if it's not null, only then proceed. But here we don't care. We just take it, add 1 because we want to keep the \, dereference the thing, and then make it null, effectively just cutting off the file name portion of the string. Now we'll allocate 2 additional paths. My exit path, let's call it, and the other one will be the DLL path. WCS CP CPY. So wait, first the target, then the source, and then WCS cut, which concatenates. It adds a string to the end of an existing string L, and it was called hook test. Oops. Hook test. And the other one here, I forgot the semicolon here as well. We'll just have the hook DLL, DLL.DLL. Okay, this will give us the two paths we need. And let's first just start the project. So there is a couple of functions in Windows which is used to start projects. You can either use create process W or create process A. The difference between the A and W APIs is the A is an ASCII API, so it takes a narrow char, a string, while the V version takes a wide string which supports Unicode. And there's also a shell executex function which you could also use, but here for simplicity let's go with the create process W. And of course there is another create process function on the NTDLL, but that one is much more convoluted, so it's not recommended to be used. The normal create process function lives in the kernel 32 DLL, or nowadays the DLL was split into a few DLLs, so it's the kernel base DLL. And this, by the way, is another target which one might want to hook. So if you would have an application that starts something else and you want to either make it not started, or you would want to make it start something different, or you would want to change the parameters with which it will start the other process, you could hook the create process W function and then change whatever then would be started. Null, and then well, we have a few parameters. So command line we don't pass any. Security parameters we don't set. Thread security as well. So it will just set the defaults if we don't set anything. We don't want to inherit any handles. And then here we can specify creation flags. For now, let's go with 0, but we will change the state at something else. Environment we can specify null, then it will create a default one. Current directory also. Then it will take our own current directory, and then we need to specify two additional structures which we need to first define. Startup info v se, and we zero it out. And the other is says information pay, which we also zero out, although we don't need to, because it should only be relevant if it should only be relevant if the call succeeds, and then should be filled on its own. But it's good practice to null out memory so that you can easily see if something has yet been initialized or not. And this will so we don't the startup info we don't really care for what's inside. We could specify here window title, positions on the screen where to open the thing, some other parameters, show window is whether it's maximized or minimized, some more reserved things. Here we could specify pipes if we want to intercept the console output and or provide own input, so such things. But for our use case we don't care for anything of that. We will be caring for, however, for the return values in process information, but for now we will just close it. So close handle, because it gives us two open handles as it comes out. So one is the process handle and the other one. So when a process is created, it is always created with a first thread. So the other thing which we want to close is, of course, so we want to close both of them so that we don't have a unclosed handle in our process. Of course, since we terminate our process here, it doesn't matter. The operating system would close the handles on process exit for us anyways. But if we would have a program that is supposed to run for a longer time and do some things and so on, then we would not want to leave open handles, because that they would accumulate and at some point the application would crash. So now when we run it, it will just oh wait, something went wrong. Yeah, it doesn't like FootCS CPI and doesn't like FootCS cut because they are unsafe. Because basically they don't check whether there is enough space in the target memory to write actually to it. So we can use the S version, and this just takes the destination size in words. Size in words. Okay, so array array size of this and the same thing here, just with Excel, and then let's go S, and then of course we have the same issue with cut, that it needs to we need to use the S version where we specify how many things we are allowed to put in. And if it said that something is in words, then it means the units of whatever we are dealing with. It doesn't mean in word as in 16-bit integer, as would be the type word. But in case if we are working with strings, it really would want the word size of a string, which would be the byte count of the individual character. So either 1 or 2. And here then we want the count of those white bytes. And array size is a precursor macro, which is quite nicely implemented. If we arrive at the implementation, here it really just takes the size of the first element in an array, and of course, since all the elements are the same size, this is represented. It's the other way around. Number of, it should do somewhere. Yeah. Well, they are simpler implementations of that. Let's make an own one. Hash define r count. Let's call it r count. And the way that this can be implemented the easiest is just size of the value size of x. So size of x, if we call this with an array, will give us the size of the array in bytes, but we want the word, so we divide this by size of x0, and this way we get the count of the elements in our array, and this is a much quicker implementation. I'm not sure why the modern implementation of array size is so convoluted. There are probably some reasonable formal reasons why they changed that and made it so complicated, but usually when you have some older headers, then this is the way such things are implemented, because it's just very straightforward. Okay, so we try compiling it again, and what it will do is, okay, so do you want to fail? No. Now we have our warnings, and then we have the application ran fine. Okay, so at this point we just started the process. We have not yet done any modification, so what we will want to do is we want to somehow change the behavior of the application, and this is actually a bit tricky, because in this case this is the very first thing that the application does. So we would want our hook code to run in the application before anything else runs in it. So there are a few ways how this can be done. Let's start with a maybe more exotic way. Yeah, that sounds like it's a good plan. Although on that, yeah, let's start with. So let's create a function. But before we do this, we will just add for testing here into a DLL. Although actually, we can just directly call our hook message box in the process attached. We don't need to add some dummy code or anything. We can just really just do it, and then we would want to here break. We want to unhook on process detach. Of course, this is not safe, because there might be other threads being executed right now, and also it's also not safe. The hooking is also not safe, because here the same issue applies. Other threads might be in the process of using the message box function, so if you want to hook it, we really need to be sure that nothing else will use it. And if we do it like at the very beginning of the program's execution, then somewhat safe, because we know the programs did not start doing anything else, while the unload, if the unload is forced on the application for some reason on a later point, then what it would do is it could much more likely run into errors. Effectively here, probably this will only be executed once everything in the program terminated anyway, so it should be fine to leave it there. Right. So there are many ways how you can force an application to load a DLL. We will be trying one now, and then we will add a few more complicated ways. So right, inject DLL, comma use APC. This will be our function. It will have multiple functions, inject DLL, and then which method are we using. And APC stands for asynchronous procedure call. This is a mechanism in Windows that allows us to execute things doing certain transitions from the kernel to the user mode. And I think that should be there should be one of these transitions before anything interesting happens in the entry point of our function. So we should be able to use this. And here we'll add this process information as a parameter. So as a parameter or as a meta. And of course the DLL path is also an important value, since we want to know where to what to inject. Okay, so we have this, and the way this works is first so we will be using the we could also make this, doesn't matter. Let's make this boolean so that we can return a success or error. And the way this works is there is a function QUser APC, which takes a function pointer, so an address to execute. Then it takes a thread in which to execute it. So the thread we can here go for the one thread which already has been created, and we can specify an address for data. So data address will of course be our DLL to be loaded, and our code to be executed will be the address of a function which is already present in every binary once it's done loading. That would be the kernel32 function load library. So of course the address in a target process might differ from our own process, but effectively this will not this is very unlikely to happen, so we don't need to worry about this scenario. If we would be worried about it, we could go for using some anti-DLL function, but the problem here is that all the other more low-level functions for which we could retrieve a reliable address at early process creation time, and those functions take more than one argument, and the limitation of create user APC is that we can only pass to it the first argument and nothing else. So that would complicate things. There would be ways around it, but for now let's try to do it simple. So first of all, we will want to allocate some memory in our target process, because we need somehow to communicate the path of the DLL that it is supposed to be loaded. So the simplest way to do it is to allocate memory in the other process and write then our path directly there. So size t. Then we need to know how much memory we need. VCSLen. I hope VCSLen works without any complaints about security, because this is just a read-only function. So VCSLen from the path plus 1 for the terminating null, and this times size of char. Okay. Stern and res virtual alloc x. So we know virtual alloc from before, but virtual alloc x takes a few extra parameters, and most importantly, it takes a process handle so that we can operate on foreign processes. Here for address we say null, which means it will just pick an address on its own. Len cos len, and then mem commit, and the protection is page read write. We don't need execute because it's just an argument. And then of course write process memory, which takes again a process handle. What comes to our aid here is that the handle we get when creating a process is an all access handle, so we can do pretty much anything we want. Where address is address. then we provide our own buffer, so with asterisk DLL path, comma, length, how much to copy, and then it would return us a value that would tell us how many bytes it actually copied. In case we would want it to copy more than it can, for example, we allocated not enough memory, then it would not just completely fail, but it would do until some point, and then it would fail, and then it would return us that it didn't do everything, and it would tell us how many bytes it managed to complete. But we don't care for that information, so we just pass null to it. Okay, so and now we need, of course, to find the address of the load library W function. And what helps us here again is that to save memory, the way Windows works is that even if you have DLLs which are configured to use dynamic base addresses or random base addresses, this only applies for when the DLL is loaded the first time. And then once it is loaded, then all the instances of the DLL will share the same copy of the DLL in memory. This is implemented using a copy on write mechanism. So every process that loads a DLL, in principle, can write to it, as we did with overwriting the message box function in the user32 DLL. But effectively, what we did not change it on the system level. So what happens there when you try to modify a page is that the page this one single page gets copied into your process so that you get an exclusive copy, and the memory layout is adapted within your process. The memory mapping is adapted such that all the other pages of the DLL which have not been modified are still shared, and only the pages which you are modifying are replaced with your own personal copy that you can modify. Yeah. So anyhow, the thing is that since we want to reduce memory by sharing as much of the DLL as we can, the DLL must have all the same values, and sometimes you find a lot of things how a DLL is written normally have not just relative addresses but also absolute addresses. So for example, all the character strings are loaded under some absolute address, and then when they are referred to an absolute address with this abs move function are loaded. So if every DLL would be loaded on its own to a different memory offset, if the memory offsets of a DLL would be different for two different processes, then they could not share the same binary image of the DLL. That's what I'm trying to explain here. So since we want, however, to save memory, effectively, once a DLL is loaded, even if it's loaded at a random address, for every subsequent process, it will be mapped into this process with the same address, at the same address. So for us here, the simplest cheat is to just take our own address, void stern, library v, and it will be valid for the other process. This trick does not always work. So if our own process is, let's say, 64-bit and the target process is only 32-bit, then we do not have an own copy of the 32-bit kernel 32 DLL, hence our addresses will be all wrong. And the other way around it also applies. So there in such a scenario, one would need to use a more complicated workaround. But in simple cases, such an approach is good enough. So we have our target address where to jump to. That needs to be cast to the right type. That takes apc func, I think. Func. And of course the argument will be the address of our string. So if we go back to here, as we see, this function is super convenient because it really takes just a single argument, and that's it. So this is really nice. It's just an address, and this we can pass perfectly fine from using such a function like this one. ptr, we just need to cast this to the right type. Okay, and when we run this, in principle it should work. Let's try it out. Not quite. We forgot to return a value. Should also check whether this was okay. So bool, okay, it's like boolean is a preprocessor definition for integer, because for some reason the Windows API uses integers for boolean instead of chars. I mean, the reason will probably be just historic, that that was a standard return type. But if you have just a bool, the easiest way to convert something that is an integer to check whether it's null or not is just to negate it twice, in which case, because if you just would return an integer as a boolean, then the compiler may complain that you're losing data because you're casting something that is 32-bit or something that can be at 8-bit at most, and officially just 1 bit is used. But if you negate it twice, then you kind of really say you just want to check it, and when the compiler is smart, it will of course optimize this away and then just return you well, it will actually not quite optimize it away. It will really ensure that the return value, so the boolean should only be 0 or 1, but you could return 2 or 3 or any other number, and negating it twice will really ensure that you will either get 0 if it was 0, or you will get 1 if it was anything else. Okay, so let's run it again. And voila, it worked. Up is running fine. All the other messages have been suppressed. So let's see if we can. This is not. This is missing. Also, we did one thing wrong further down. We should fix that. Child process debugging. That sounds like it's the right thing. Okay, we need to restart it. So let's close and reopen it. So the extension which we are installing now will allow us to automatically have a debugger attached to any process which our main primary process creates. So this way we can easily debug our target without having to manually attach to it. So what we have forgot to do in our code here is it somehow still worked. I will just run it a few more times. Apparently it works each time, every time, but actually it shouldn't. So the thing is, here we should have specified create suspend, because basically when we as soon as we do this, then the process will start doing things, and our hook function here apparently was fast enough that we managed to get it in the process, and the process managed to execute it because it actually before it actually reached its entry point. But if things would be slower, then the process would be past the first part of the code, and then it would be in the entry point, and then it would be doing things. So what we want is we want to create it suspended so that it will be created, but the thread in it is held in a state where it doesn't execute any code. And only once we have prepared our code injection, then and only then we would actually resume it. Resume thread. PI thread. But as said, here it will now just work properly, but we just were lucky that worked without doing it. So if this would be slower, then it would not have worked. Okay, but let's go to a DLL and put a breakpoint there somewhere. Yeah, here. And run it again. And I did not enable. I installed the extension, but I need to enable a debug. Child process debug setting, enable save. Now it worked. And voila, it attached the debugger to the new process we created, and now we can break inside the DLL of the second process. Here, let's again load symbols. I should enable loading symbols always. That's not here to enable. Tools, options, symbols. Rather module symbols. Yeah. Okay, so you can inspect what is happening here. So every thread starts its execution somewhere in the NTDLL, in the loader initial thunk, and then it does some things, and here it is called a kernel base DL function. So I said this in the past would be part of kernel 32 DL, but they have split that at some point. And this is of course our injected address. So everything that happens from here upwards is the result of our doing, of our user APC that we have queued. And here you see this RTL dispatch APC is a function which checks which queued APCs they are, and it will run them one after the other. And this happens very early during the process initialization. So if we look in a more advanced task manager on our, just sort it by start time, on our target process, we see that it has a main thread, and here in the main thread we are in this hook DLL, and we only have 2 more threads which are part of a worker pool created by NTDLL to load DLLs more efficiently. So it loads, it is able to load multiple DLLs in parallel. That speeds up process startup. And when we go to our hook test, we can put a breakpoint here. And if we now resume from our other breakpoint, at some point we end up here in our main. So we see that our code, our DLL, was executed a long time before we started actually executing any code here. It's not loading all the symbols. There a load always load symbols. Now we already enabled that. Maybe it needs to be restarted to take effect anyhow. Yeah, but that's the whole trick. So we can make a program execute a code block or execute a function before it actually will start executing its own code. So this is quite a powerful ability, and this way we don't need to be able to modify the original program to effectively modify how it is behaving and what it is doing. Of course, we are mostly limited to modifying how it interacts with the let's say with the environment, with the operating system and other libraries. We cannot easily modify internal program logic, because for that we would need to understand what the program is doing, which would be much more complicated. But in principle, from such an injection DLL, if you would know the right offset in a program file to modify it to make it do something else than what it is, than what it would want to do normally, then you could do this as well. Okay, so any questions? No questions? Okay. So if there are no other questions, then next thing that would be, I guess, quite interesting to see is how would we do it if we would not want to use this APC mechanism. So there are scenarios when one might not want to do that, and I said there are many ways how you can inject a DLL into a process. Another option is to use the create remote thread function call. We could try this out really quickly. So we'll comment this out, and we will call this thread. So we just actually we can copy to a function and then just change a few things inside. So a big portion of the idea is the very same. We just allocate memory, write the address to it, but then instead of using the user APC, we will create a thread in the other process, and thread ist gleich create remote thread in PI process. So Windows gives you an API to create a thread in a different process, and you can specify an address within the different process where this thread should start. That sounds like an invitation for security exploits, which it kind of is. Okay, so stack size 0 because then it will take the default one, and then how is that called? LP this thingy, where we just pass our library address, and then we can specify one parameter, which will be our address here. Then creation flags null. We want the thread to run instantly, and we could get the thread ID, but we don't care for it since we get the handle. We can check here. No, doesn't matter. Let's return true. If this equals if this is equals, so it could fail. So then it would be handle invalid value. Then return false. Else, just wait for the thread to finish. Wait for single object. Hat, comma, and infinite. So infinite. Wait 12 and infinite is just -1, so we could have also written -1 here. Okay, let's try this out. Is it not running properly? It's hanging. Oh no, it's this one is hanging. It's loading symbols. Let's try it again. So is it hanging or is it doing something? Does not quite work the way we wanted. Let's not wait, but this is not safe. No, it's still busy loading symbols. Let's wait for them to finish. So the setting I changed earlier is that it will load all the symbols from the Microsoft servers for the DLLs loaded by the process automatically, instead of only doing it when we click on load symbols in the debug view. But it's kind of appear to be reasonable if we are messing with system files to have all the symbols so that we have more information than the function names. Okay, so it was done with that, but it did not. I think the problem here might be that when this will not start automatically on its own. And here all the threads are suspended. Somehow did not create the thread properly. Right, let's put breakpoint here and a breakpoint there. Run the thing. Okay, so now when we inspect the hook test, it is only a suspended main thread and a thread. I think this one is for the debugger. Okay, now we run this command, and it created another thread, but now all they are still suspended because we're in the debugger. And if we wait, then I think the thread terminated, or it is still sleeping. Let's see what address we have. It doesn't tell us the addresses. I mean, it tells us the starting address, but it does not show us any symbols. The other method is more reliable. So if we started now it's loading symbols again. Okay, we need just to wait. Okay, so I have disabled the wait here, and effectively what happens is it is not fast enough to intercept the first message box, but if we select no and it already had some time to do its thing, then it will work. So this create remote thread is not effectively it's not fast enough, it's not reliable enough. I'm not quite sure why this doesn't work, because usually that should work and be fast and not hang here in the execution forever. I think this the child process debugger is breaking things. I have disabled it now. Let's try it again. Yeah, now it works fine. So if this if we enable this, then it breaks the mechanism that is needed for this create remote thread to be executed without a delay fast enough. Because here, when we run it now, it will just execute the thread, and once the thread is finished, then it will only exit the function, then resume the actual main thread of the function. But at the same time, this makes the debugging more difficult. So if we would want to do that, what we could do is where were the flags here? We can create our own thread suspended. Resume thread. Put a breakpoint here. So now we are doing as if we would not have the the child process debugger. So we go now to our testing, and we see, okay, now we have only the main thread and another thread with a is this? Let's see. F7 FF. Yeah. So wait, is it? No, 80. It's not this one. No, we won't see the address instantly, because first it will have the address inside the NTDLL, but I'm not sure why this thing is not loading symbols. It should be showing them as well. Anyhow, the thing is, we have this thread, and now we can go to debugger, attach to process. Oh, we have another instance. There was a hook test alive from one of our earlier tests. Let's quickly terminate it. And now connect to this. And then when we put what was the DLL? Not the DLL, no. Yeah, somewhere here. Then if we put the breakpoint here, since we attached to the process, and we now it says that the DLL is not loaded, but when we resume, we end up in a breakpoint in the early process creation, but we don't care for that. Then if we resume this again, then we end up in the breakpoint in our DLL. At this point, when we go to our hook test, then we see here our thread with so this thread already was there, just we previously did not display the address properly. And then we have, of course, the main thread, which is still not really initialized, so it's not yet running. We can actually go there. Test and put a breakpoint at the very beginning. And only once we finish with this, the rest will resume here. What we also could do here is we could put a breakpoint here. This is the earliest where our own code starts being executed, or rather when the code from our application starts being executed. Because before this point, we are executing the NTDLL, and here, what we see here, this code is part of the C runtime, which the compiler brings, but this is not code that we wrote. It is code which we are just using like a library, basically. But this is the actual entry point where our process would normally start. So if we repeat the whole thing, we start. Okay, this is the entry point for our loader actually. Then we start again. Then we end up in the loader and resume. Then we need to again attach to process. Attach. It remembers the filter that you have set, so it's reasonably easy to reattach. There is also a function reattach. Somewhere. No, I think the function is only, the command is only available when we are not attached to anything. Then it would try to reattach to things it was already attached to, and it would also use some matching for the name. But it's sometimes it works, sometimes it doesn't. So if you have like multiple, if you always attach to one process with a given name, and then you terminate the process and then start the process again, then reattach, and there is only one extra with the right name, then it will attach to it. If you would have a scenario where you have multiple names, then it would not know to which to attach to, and it would just show you the normal attach to process window. But anyhow, we end up here, we resume this. Then as said, there is a breakpoint in the NTDLL which is triggered if it sees that early enough a debugger is attached to the process. So that this would give us the opportunity to add additional breakpoints if we would not have yet any set. Then we continue this. We end up in our own DLL. So here, as you see, there is no APC. There is no asynchronous procedure called dispatch. We just have the thread creation and then the thread execution. And then when we are done with this, then only, and then once we resume the main thread, actually we should put a breakpoint on that maybe for a better demonstration. Here. So after this line was executed, then we ended up in the CRT startup of our target application, and then of course we can run it. Then the C runtime initializes things. So usually, the typical things that are done during C runtime initialization, except of course internal housekeeping, the most important ones are like initializing of values for static variables and stuff like that. So at this point, when we enter the C runtime, at this point already statically linked DLLs have been loaded into the process, as this is done by the NTDLL itself during early process creation. Okay, and then of course we can continue, and then we have our success message. Okay, any questions? No questions? Okay. Then let's proceed with the third method of injecting code. I mean, there are more than 3 methods, but these are the methods. These 3 methods are the ones I like most. So the third method is significantly more complicated. It's called thread hijacking. So again, we start just by copying our standard function prefix. The idea with thread hijacking is that we will take control of the main thread, so the one which usually would start in here, but we'll take control over it before it actually starts here, and then we will do our own thing and then return the control flow to the other, to the main thread. So in this case, this is a more reliable method than this and this DLL than this thread injection. As we have seen, this can be disturbed by other things, but the asynchronous procedure call is still superior because it's really simple. The main reason to demonstrate this thread hijacking is because there really is no simple way to do the thread hijacking. So you need to write and inject some shellcode into the process. So this is significantly more sophisticated of a method, and of course you could use an own shellcode block together with a asynchronous procedure call or a own thread. This would be the method which you would need if you would want to, instead of load library W, to use the LDR load library LDR load DLL from the NTDLL DLL. So if you would want to do some really low level things, then that would be the right approach. And the fancy thing about this is that if you have a 32-bit process on a 64-bit system, the process will still start its existence as a 64-bit process, and it will always have a 64-bit NTDLL loaded. So there are things that you could, so in principle, if you take control over the process early enough, you could have a 64-bit DLL doing something inside a 32-bit process, but this we will not do. That is even more complicated, and usually there is no good reason to do it. So in the most cases, what you would just do is you would have a secondary injection DLL which is made for 32-bit, and you would just inject the other one. The only reason why you would need own shellcode here is that you would not be able to easily resolve the load library function. What you also of course could do is you could have a 32-bit helper program which just runs and returns the right address, and then you just reuse that address. So that would be the simple and hacky way of doing it. Okay, so let's proceed with this approach. So we will create a helper variable context that is a huge data structure which represents the entire state of a thread on Windows, at least the aspects of a thread which user mode applications are allowed to modify. So as you see, you have a couple of addresses, then you have some flags, some more flags, then you have the segment registers. Some of them you actually cannot modify. You can read them, that's why they are here, but you cannot modify. You have the debug registers, then you have the actual integer registers, which we already know from the different assemblies which your program operates with. We have the very important instruction pointer. Then we have the registers for the floating point units and the vector units. So basically everything that defines the process, the thread's state, and everything that is saved and restored when threads are suspended and resumed, respectively, when threads are switched, is stored in this context structure. Okay. So we have our context structure. Let's call it CTX. And we have to use one of the control registers to specify what we want to do, or the control flags. Control flags. There they are. I must have mistyped something. Context control. Context control. Get thread context. Thread. So that's the handle to the first thread that was already created for us, and then just give a reference on CTX. And everything about the not yet running but freshly created thread should be stored there, and we just make a copy of the last error in case there was one, so that we can inspect it in the debugger. And basically, ultimately, what we would want to do is ctx.rip to set this to some other address, and then write the thing back. So okay, it equals set thread context. It takes the same arguments, I think. And we can also take a copy of the error just to see if everything was fine, and then now the whole exciting thing happens in the one line which we have not yet filled in, and for this I will create another function which will be called write shellcode, and it will write the shellcode to the target application and return the address where the thing is supposed to jump to. So write asterisk write shellcode. What is the address? And here handler h process. Oops, handle is capital. Then the word64 at return address. So the address where it should jump once it's done doing its own thing. Then const DL path, so which DL should be loaded, and if we would want to be extra fancy, we could have a const char name. Oops, it's not typing. Const char asterisk func name, which would contain a name of a function inside the DLL which we actually want to execute. So while we could of course have a DLL that here whenever it's loaded that just does its thing, we could also have an actual exported function in the DLL which will which then when the DLL is loaded by any other process will not do anything. It will only do something if we explicitly jump to that particular function name. But here for simplicity, for now we will just implement the function step by step, and the first thing will not be the name will not be yet relevant. So pi.process, the return address is ctx RIP. Oops. ctx RIP. So the old value basically. So we want to do something and then return to where this thing was pointing before we started doing things. And of course the path to our DLL. And we will already now specify the name which we will not be using for now. Oops. We will call the function install hook, but we will not be using this for now. We will be using this later on. So this needs to be casted on a Dwarf 64. Okay. So if we don't manage to do it in time, then we will just continue in the next lecture. So one thing we can copy from here is this helper structure. This is super convenient. We will be using this when assembling our shellcode as well. Okay. Then let's create a buffer. My shellcode. Let's make it 1000 bytes long for now. We will later only copy the amount that we need, but just for convenience, let's just allocate more than is needed. Code.pb is equals my shellcode. Good. We could, in principle, also allocate the DLL path in an own code block, if we want. Or we could allocate everything together in one large code section. It's more elegant to, I think, have everything together. So for now, let's not. This will be done at the end. So let's copy a few things. So this a few things we will need to do at the end. So like allocating and writing thingies. And we'll need a few addresses of functions. So which then idr DLL is equals so we're using here get process address, get module handle to get some addresses from the entity.dll, comma 1 is ldr DLL, and the other one is get procedure address. LDR get procedure address, just that they are with the capital L. So the first address, the load DLL, is equivalent to load library W, and the LDR get procedure address is pretty much equivalent to the get proc address, just that get proc address is in kernel 32 DLL, while this one exists on the NTDLL. So this shellcode as written here will work even if the kernel 32 DLL is not yet loaded, which is admittedly a very edge case, but it's always nice to have more flexible thingies implemented. So we have the two addresses, and then we'll need to, for convenience reasons, we will want to have a place in our shellcode where we can store thingies, and that way is how we can do it. So first of all, we can of course just define the top of our shellcode to be our data area. That's one option, and the other option would be to and then we just return an address somewhere in the middle here as right shellcode. And the other approach would be, of course, that we directly return some address from the middle of our shellcode. We could maybe try to make this here a bit more elegant, so that we have the data section. So the downside of having the data section at the very end is that if we don't yet know how large our code section will be, then we don't know where the data section can start. So this is a negative aspect. And the other thing is that if we do it on the other hand on the very top, then we would first need a jump instruction to jump over the data section to our actual payload with the code. So I think we should start with that approach. And what we should add to our bytecode will be some interrupt, so that we can debug it if we want to. So first we will add a null xcc opcode, say int3, and I forgot the equals, and I forgot the asterisk. Right, and what we also might want to use instead is no-op. So no operation is 0x90. But for now we will comment this out. The idea is that if we switch between those two, we will not shift any offsets in our code. Although the actual idea of the way we will be generating the code here is such that we will avoid having a hard-coded offset, so that we can easily modify the code, and then while the thing is generated, the offsets will be generated correctly for us. So just to help us, we will write down the addresses where we are at every point in the code, at least at the head. So we have this. Then the next thing what we this one, right. Next thing we'll want to have will be a relative jump. So where's our compiler? So what we want to do is .mp to args plus 0x1 2 3 4 5 6 7 8. I just use the pattern here so that sorry, not args plus, we wanted RIP plus 0x1. Is that too much? No, it should be working. When I do a jump, I don't need to specify anything. I just tell it to jump by how much, and it will jump relatively, I think. This is not quite right. I need to add a square brackets. That's what I forgot. RIP plus square brackets. Yep, now it works. 1 2 3 4 5 6 7 8. Okay, so So this is the jump instruction, and the rest is by how much. So asterisk code punct pivot plus is equal 0x. Then we need to switch the order. We will write down what we have written. And the next thing will be code punct double word plus is equals, and this will be the actual offset, which we don't yet know. So let's leave it at 0, or let's leave it maybe not at 0. Let's leave it at let's leave it at 100. 120. Let's go by 100. Doesn't matter. And now, so that we on the safe side, we'll just here reset this plus equals 100. That is not quite right. So we have to get this right. First of all, we have here already 1 byte written, then we have here 2 bytes written, and I think it takes the address before the thingy, so we actually would want to jump to 102. We will test it. Let's re-enable the child process debugger, because without that it will be, I think, annoying to try it out. So what we'll do here is we'll just put another breakpoint. Yeah, so we reset sc is actually we could also write it like this. Doesn't really matter. And here we then start at probably 102. We will see whether that is correct. And yeah, so let's just allocate the size of our buffer. We don't need to be, I mean, we could, let's do it smartly. So length would be sc. Sc is this one, that one's we got, so 9 byte minus sc. Because the thing is, in bytes, and it's incremented each time we add something to our shellcode. So if we just from this subtract this, we'll get the count of entries that we need. Which alloc, so we allocate, we try to execute. We don't need actually write, so page execute read without write. We can make it safe. Process address, and now here we pass to it our shellcode. And we said we want as a return the address to jump to, which will be the address which we have allocated. So the shellcode should be pretty trivial. It should drop us in a breakpoint and then jump to the next breakpoint. And what is also good practice is to just add some knobs at the end, so that if we jump not where we want to, which by the way is another dirty hack approach, is that you just, if you don't know exactly where to jump, but you know that it will be within a certain range, you can just knob out everything and then have your rest of the code. And if you where you jump inside of your knobs won't matter. So we will actually now test whether we jump the right offset, but if we jump the wrong offset, then we just end up in one of the knobs, and then we need to adjust it. Okay, so we are in the start of our own thingy. Then we resume the thread, and then we are at a breakpoint, and this is our own C instruction. Then we have our jump. So let's do step, another step. Oh, and we ended up completely somewhere wrong. That's not good. Our jump is not correct. Let's see why. I mean, I have 1000 bytes allocated. Okay, I mean, I can go with a whole page. Okay, double word. Yeah, double word is the right one. And we can, for testing, just add here 100 and see how this looks. So we have, yeah, this is 100 hex and this is FF, 5FF. That should be right. It jumps at the instruction pointer. It should be direct. Let's see why let's see what is failing exactly. So we ignore this. We ignore that. And now we enter our breakpoint again. So yes, view disassembly. So let's write down our starting address. Okay, and this looks like the right instruction, and it says where it would jump. It would jump to this address 0x, and if we subtract the one from the other, then this one should be the bigger one minus this one. Right. Copy and paste here. So this is our starting address, and this is the address we are jumping to. That looks like we're jumping the wrong direction. And we're jumping too far. The annoying thing is that the thing here is eating out away our zeros. Not there. It's fine. No, that should be right. It just shifted slightly too much. So we end up, if we take the difference from the jump target minus start offset, yeah, we end up jumping by 107. Why is that? Well, first of all, because we have here 1, 2, 3, 4, 5, 6, 7. So it takes the end address, and we did not count those bytes to it. We just counted the first two, so that's the problem. So this will be then 7, 2, and here 4. This one not quite right. This thing here is 2, and this is 6. No, it's fine, it's 7. So we go to 7. And then it should be right. Let's try again. Continue. We don't care for this breakpoint. Continue. Okay, view disassembly. This should not change. Step. But it did not jump where it should jump. No, but that is not correct. We don't want the... just want a relative jump. That should not be in square brackets. This does not... this compares as well, but then it does not take into account where we want to jump. Respectively, it creates an absolute... Let's check the documentation for the assembler. So a relative jump in Stack Overflow. So this is not the syntax of our assembler. That could be the right syntax. The annoying thing is that the different assemblers have also different syntaxes. So plus 100. Nope. But this one we already seen. I just want a normal relative jump. This will not be a real opcode probably. Yeah. We don't want an absolute jump because we don't yet know the address where it would jump to. We want to make it as simple as possible, so a relative jump is what we want. We jump short 3 plus 8 bytes. I think if we can just make this thing generate a code that we would just take a look how this works. We could try that. This may be the simplest idea because for some reason normally it should be just jump and then but we don't want the absolute address. Let's see. We'll try something else for we just make a loop and then check how the loop what instructions the loop is using and if it has a relative jump somewhere. So we have however still a lot of boilerplate code, so for this one let's disable the unneeded stuff as well. Just method support generation, runtime checks and security off. Okay. Yeah, so we have a jump to main plus something. That sounds already nice enough. And if we disassemble this code block, it gives us a jump 0a, but this is the same thing. Did I just forget? Wait, was jump? Yeah, 0x100. This compiler is broken. It does not properly compile. That's annoying. It does not properly compile the thing that it decompiled before. Let's look for another one. There was one that could do many different. I had the link somewhere saved. Wait a minute. No. Shellstorm, that's the other one. Yeah. Okay, I will put this one also in the chat. And again, we start with our test case. A very simple jump. We check whether it properly disassembles it. So it is 64-bit x86. Disassemble, yeah, jump to A, and now we'll disassemble that correctly. And now we got let's say we want to go to 64 offset. Yeah, that works just fine. Okay. Yeah, the other compiler was broken. Sorry about that. Usually it works, but for some reason for this particular instruction it was just not providing the right output. So it's a single character opcode EB, and this thing will be now just, well, it will be 3. It will be 6. I think we will see whether the offset is right, but at least so we have jump 0x okay, run, continue. This is our breakpoint, and when we jump from here, it still didn't do the right thing. Also no, wait, do disassembly, and now we go step by step. Jump to it jumped only by 3 characters for some reason. This it jumped more. How much more? It jumped by ABCD. Okay, this one is another one, and it takes a 32-bit number. That was the problem. The other one only jumps by. The other opcode only jumps by. The EB opcode only jumps by up to a character of offset. That was the problem, and we here are overwriting the D. So we were providing the wrong argument for the operation. Okay, now step by step. Step. Well, we jumped somewhere, but we still didn't jump where we wanted to go. At least it's closer to our original value. Oh wait. Sorry, that's not complete. We also need the C8. Wait. A, B, C, D, A, B, C, and it takes a value, a short value, and that should be fine. Let's jump just by 10 for now, so that we don't go that far off. 17. That should be not capital, but it will not make a difference. Okay, so again, run. View. Okay, so we have here our code. That does not. Oh. Yeah, when I changed this to a shorter one, I forgot to change here the type which we are writing, and of course this ended up providing again the wrong argument. Yes, now it's correct. Okay, we can change everything back to 100, and that will be fine. Okay, so let's run it. Continue. Okay, so we are at our breakpoint. We do our step. Through the breakpoint, we go to the jump, and then we jump directly where we should go to the code that we have put there, and the rest, of course, then null. So if we run this, we'll end up in the breakpoint. Then we have a few knobs, another breakpoint, and if we try to continue from there, we only have invalid data because that's just 0. But I see we are running out of time, so we will continue doing the next lecture. As you see, this is a much more laborious process and much more error prone. So first run into the problem that the other did I close that? Yeah, I closed it. That the other online assembler just for some reason failed at assembling the code properly. And then when we found the right one that assembles nicely, we had the problem that here the wrong type was selected. So it's easy to make such mistakes when you are changing things that you forget to change the type that you are writing. But still, I think this way with this helper structure, it's much easier and much more convenient to write things than if you would just work with an offset and need to add each time the right amount of bytes. So during the next lecture, we will continue writing this shell code. There is a lot more to go, and we will try the approach where we have a data section at the beginning, which will just need to be large enough to accommodate our data. Actually, we could already prepare a variable for that. That will be a long data size is equal to, now let's just keep it at 100. And let's see if we jump. So here, wait, was that +7 actually correct? It looked correct, but somehow, let's see, let's count 1, 2, 6, and this is the 7th. Well, I jumped at the right offset, so it will be fine. I'm just thinking whether we can maybe... No, let's just make it like this. Just make it data size +7. Oh no, this +7 bugs me. That should be... If this 100, this will be effectively less than 100, because what we have seen here is that it's subtracted from our number. How much did it subtract? 8, 9, 8. So it made an 8, and then we had a D before. So 8, 9, A, B, C, D. It subtracted 4. It subtracted 4 from the value. Did it subtract 4? Let's ask the calculator. D in hex. D minus 8. It's 5. It subtracted 5. Yeah, that makes sense. It subtracted their own amount of bytes to jump. So it always takes kind of the address from when itself is at the end. But the value that you enter is the value that should end up in this. So in the principle, if we would want to jump by 100 from the beginning, it would be so let's write it here like jump. Now let's leave this as is. Plus data size. But this thing here needs to be shifted by the right amount so that we end up at the right position, and I think that should be 6 and not 7, although then 6. Let's see. Yeah, because let's try it with 6 where we end up whether we jump to the wrong address, and then we will see. Okay, step. 6 was still fine. So before we just jumped one line too far and we did not notice that. Yeah, 6 makes sense. And now what we also could simplify is because because if we make the difference of those two, then we should get the number 6 out. So I'm thinking how we can... Basically, we could just make here plus data size, and that will do it already. Plus, this will be here. Yeah. Because this will be nice, because then we can make the data block as large as we want, and we only need to update the one variable, and our job will already always go automatically to where the data block ends and when our instructions start. I pressed play once too much. Play for debugger as we close, and then we go step by step. Yeah, nice. Okay, so we improved on that. So that's since we are out of time, then we will stop here and we'll continue with implementing the actual executive part of our shell code during the next lecture. If you have any questions, you can still ask them. If not, then we'll see each other next week. Bye bye.